some of this? Here. We just wrote 9 factorial on the board. There's a quick way to do it on your calculator. So let me show you. After I hit the 9, I hit the math key. But I don't see it. But if you hit the right arrow, all the way over to the next one is number, and the next one is complex. But the PRB, guess what that stands for? Probability. And look at choice number 4. Right? 9 factorial. It'll do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 very quickly. Yeah. So, in your book, I think the second question that they ask that I assigned, they say, hey, suppose you have a baseball lineup. You're the Indians manager today. We're all managers when we watch the Tribe. We are. We want to take over for Wedge and say, listen, buddy, we could win more than you. We'll change the lineup. How many different ways could we rearrange those 9 people? Well, there it is. 362,880 ways. If you pick the right lineup, you might win. Isn't that amazing? Oh, it's question 5, I think. Here.
Oh.
Question 6?
No, this is complement.
Oh, keep going. I know I saw it. No, it's on that page. Page 189. All right. All right. We weren't. We weren't. We're doing it now. 4-7 was on counting. There we go. I said don't do it. You guys followed directions very well. The reason I'm not having you do it is I really wanted to kind of do it with you. So here we go. What problem is it? Page what? 189. Page 189. All right. Let's get this going. Page 189, number, and where is it, the baseball one? Number 6 says, how many ways can we rearrange a baseball lineup? Are you surprised how many ways there are? 9 factorial, which ends up being, what do we say? Is enormous. Wow. Let's answer number 5 while we're at it. What does number 5 ask? Yeah, do you understand what they're asking? I have 5 test questions I'm going to give you. I could rearrange them in any order I want. How many ways can we arrange 5 things in a line? Well, that's 5 factorial, which is 5 times 4 times 3 times 2 times 1. And what is that? That's 120. And we did 3 and 4 yesterday. Yes? Oh, I don't care. Join any group at this point. Actually, there you go. You and Emily. You and Emily will be group 5. You and Emily, Tyrone. Got a group. Great. Now, if you read, for example, something like number 7, what does it say? What are we supposed to count here? Cards. Oh, we were just dealing with cards, right? So it says, find, in the game of blackjack played with 1 deck, a player is initially dealt 2 cards. Find the number of different 2-card initial hands you could be dealt.
All right, so there are 52 cards. I am dealt 2 of them. How many different ways could this happen? Okay? Well, here's what happens. Let me explain this to you guys. Because there's a follow-up question. Maybe more interesting question? More interesting question. What is the probability that I am dealt? Guess what I'm going to say. Oh, so we don't play blackjack. Do you guys know blackjack? How many know the rules of blackjack? I just want, before I go off on this example, okay, how many really don't know the rules of blackjack? Okay, so yeah, this is not the best example. It works for about half of you. In blackjack, you win if you are dealt what's called blackjack, which means you get a 10 and an ace, or a jack and an ace. That's why it's called blackjack. Or a queen and an ace, or a king and an ace. And why? Because the 10, jack, queen, and king are all worth 10 points, and the ace is worth 11 points, and guess how many points you're trying to get? 21. Actually, blackjack is also called 21 sometimes. Well, if you want to answer a question like that, like what's the chances that I'm going to get certain cards? Well, you need to know how many different sets of cards could I get. So how about I say this? What is the probability that I am dealt the ace of spades and the jack of spades? Okay. So if you wanted to compute that, we could figure it out, I guess. You win if you're dealt the ace of spades as the first card, and what else? The jack of spades as the second card, right? So you also win if you're dealt the jack of spades as the first card and the ace of spades as the second card, okay? Questions like this that you might be interested in are not so simple. You're going to have to be able to count the number of ways that you might be dealt different cards, okay? That's kind of the idea. So here's what I'm going to say. To compute this, number 7, it says that what we need to compute is what's called 52C2. This means 52 choose 2. The C means choose. There's a formula for it. Here's the formula. NCR equals N factorial over R factorial times N minus R factorial. And I know that's really ugly. It has lots of factorials in it. But here's what it means. If I'm trying to compute 52 choose 2, what it means is I need to compute 52 factorial over what? It says R factorial. R is the number right here, so what am I going to write? 2 factorial. And then what am I going to write in parentheses here? 52 minus 2 factorial. Now, most students don't write that. They just kind of figure it out. They say, look, it's 52 factorial over 2 factorial, 50 factorial, right? And what the point is that these bottom numbers always have to add up to whatever's on top. Do you see that? Because if you take r and n minus r and add them together, you get n. So this is 52 on top, so I'm going to have a 2 factorial down there and a 50 factorial down there. And that's what 52 choose 2 means. What the heck does this equal? Huh. Well, I guess now that we know how to do factorials, we can compute it. 52 math probability factorial divided by, and I'm going to put an open parentheses here because I need to divide by both of these things. 2 factorial. Of course, funny thing is, what's 2 factorial? Just 2. So I guess I didn't really need that. Times, and what else do I need? 50 factorial. 52 factorial divided by 2 factorial times 50 factorial equals, wow, there are 1,326 different ways that I could get 2 cards dealt to me. Yes?
How do you get the guesstimation on that factorial?
That's what I was trying to show you guys. Hit the math key. So like, let's say I'm doing 52 factorial. Hit the math key. Move over until with the right arrow until you get to probability. See that probability? And then it's choice number 4. So if I move down to 4 or if I press 4, it'll type that factorial for me. Hey, by the way, this is a really cool number to see. 52 factorial. What does factorials count again? Remember, I did it up here. Factorials count numbers of arrangements. Numbers of arrangements of 9 people in a line. Because that's my batting order. And that was this. 52 factorial? That's enormous. But you know what I'm counting? What do you do before you play blackjack? You shuffle the cards, right? I'm counting how many different ways you could arrange those 52 cards. And what did you get for an answer? What does that mean? Really big. 8 with 67 more digits after it before you get to the decimal point. I can't even say that number, it's so big. That's how many different ways the cards might be arranged. And I'm going to get the top 2. And so you say, well, what are all the different possibilities for what the top 2 might be? We figured that out just now, doing 52 choose 2. This means that when you get your top 2 cards, you're going to get the ace of spades and the jack of spades. Well, that's one of how many possibilities? 1 out of 1,326. Because any 2 cards are equally likely if you shuffle, right? So by computing that this equals 1326, we're able to say that the probability is 1 out of 1326. Is that okay? Well, the ace of spades and the jack of spades is the event, right? One event. The event is that I get both of those, that there's one way of that happening. You pick them up and those are your cards. Does that make sense? And remember, these formulas work if all the possibilities are equally likely, which we're saying they are.
So if it's that then instead of and, if
what if so the question you're asking, let me hear your question, Kate. What is the probability that I'm dealt the ace of spades and then the jack of spades? Oh, now, or is different. Because if you say or, I'm thinking you're only picking one card. So that's a different problem. You're saying and then the jack of spades. That would actually be less likely. Because the way I have this worded, if I pick the jack and then I pick the ace, I still have blackjack. See? So there's a difference between what Kate is saying and what I'm saying. Kate cares about the order. She said the ace of spades, then the jack of spades. I'm saying I don't care what order I get them in. I just want to get them both.
But if they're coming off the top of the deck, wouldn't it be the same chance? If you grab one and then the other? No.
I guess what I'm saying is I don't care which one I get first. All I care about is that I get both of them. But if you care about which one you get first, there's two different ways it could happen. Does that make sense? I want to come back to Kate's question very soon. But let me say something about this notation here. When you guys see this C that means choose, choose means, and this is very important, we do not care about the order. We only care about the group. Do you know what I mean by the group? I only care about what my two cards are. I don't care about the order in this case. I don't care which one I pick first, which one I pick second. So that's how I count. When I care about the order, that's what you call permutations. And as a matter of fact, this factorial up here, when I talk about arrangements, I'm talking about how you order the 9 people, right? I'm not talking about it's the same group every time. I'm talking about ordering. So there's two different things we're counting. Sometimes we're counting how we order things, the arrangements, and sometimes we're counting groups. And I think we'll understand this as we move through more examples. Matter of fact, those examples that are right there are very good. So maybe we should do a couple more of those. Oh yeah, question 11 is a nice question. The Virginia lottery, I think, has the same rules as the Ohio lottery. Has anyone ever watched that Ohio lottery being picked on the television? They have the balls bouncing around, right? It says here, the Virginia lottery, you win if you select the correct 6 numbers between 1 and 42. Is that what ours is too? There's like 42 balls. I don't know. I don't play. But if you pick the right 6 numbers, you're the winner. Does it matter what order you pick them in? Not for the lottery. You just pick them. Whatever order they come up, if you have the same ones, you're a winner. Now it says here, let's figure out how many possible combinations there are for the lottery numbers. 42, choose 6. All right. So I guess I need a new slide here. So question 11. 42, choose 6. What does this mean? 42 factorial over 6 factorial, because that's the number right here. That's the R. Times 36 factorial. How do I get the 36? Well, I need these two numbers to add up to 42. That's the way I do it. I know you can subtract, but that's how I do it. And if you work out what that is, you'd have the answer of how many ways. Now, by the way, I want to show you a cool thing you can do with your without the calculator. Watch this. What does 42 factorial mean? 42 times 41 times 40 times 39 times 38. Do you really think I'm going to write all this out? I'm starting to, aren't I? And then I'll go dot, 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 all the way down to 1. Yeah, Jeff sees what I'm talking about. If I were to write 6 factorial, what does that mean? 6 times 5. See, I don't mind writing that one out. Right? And now if I write 36 factorial, because it says times 36 factorial, that's 36 times 35 times, can I put dot, dot, dot? You guys know what I mean? Okay. Times 1. And what Jeff was noticing, or maybe have you seen this before or no? Well, that's cool because this is neat because everything's being multiplied and you're allowed to cancel fractions when everything's being multiplied. So see how this 36 matches up with that 36? And that 35 matches up with that 35? Okay? Etc. So, really, you could just work on this fraction. And there's your answer. I mean, is that much easier? I don't know. In the last problem, it would have been easier. What was the last problem we did? 52 over 2 factorial times 50 factorial. When we did 52 choose 2, it was 52 factorial over 2 factorial times 50 factorial. So this is 52 times 51 times, and then all this is going to cancel with what? The 50 factorial here, right? That 50 factorial will cancel with all that. And so we could have done the last problem by doing 52 times 51 over 2. Let me try that just for fun. You get the same answer? 52 times 51 divided by 2 is 1326. And by the way, one last shortcut that I have to show you. If I type in the 52, and instead of hitting factorial, watch this. Let's go to the same menu. We'll hit the math key and go over to probability. Did you guys notice choice number 3? It says NCR. It'll do it for you, the whole formula. 52 NCR, you already typed in what N is. Guess what I have to type in now? Yeah, R in our example was 2, 1326. So that's kind of nice. You can do this choosing without having to do all the factorials. It's all programmed in there. Jesse. Yeah. Did you have parentheses in the denominator? You did? I don't know. I'd have to look at it. I don't know what the difference is. But let me do this. Let me do 52. Oh, no, not 52. We're trying to do the lottery. How many are there? 42, and we want to choose 6. So I'll hit math, go over to probability, and guys, it's choice 3 now instead of choice 4. Wow. Well, look, if you look on the screen, what I'm doing is I'm doing NCR with the calculator. Instead of writing the whole thing out like I did up here, right? Okay, it's a quick way of doing choosing. Yeah.
I understand why we need like the NCR formula, like to figure out how many different combinations. But when you asked what's the probability that you're dealt the ace of spades and a jack of spades, why couldn't you do 152 times 152?
That's a good question.
Because it doesn't come out to be the same.
No, it doesn't work, does it?
But I don't understand why.
Okay. Guys, Jim asked a good question, which is this. He saw this. What's the probability that I'm dealt the ace of spades and the jack of spades? And he tried 1 out of 52 times 1 out of 52. Is that what you tried?
Unless it's 151.
Oh. It's 1 out of 52 times 1 out of 51. Because remember, the probability of A and B happening is the probability of A times what? probability of B given that A happens. Did this work for you now? Okay. It almost works.
3.77 was the one.
Yeah.
1,000 here,
Okay. Try this. There's your answer. Well, okay. Jim tried to do it by saying, look, there's a 1 in 52 chance that I get the ace of spades and a 1 in 51 chance that I get the jack of spades. Because he corrected his first error. He said, well, and if that happens, I'm a winner. But that didn't get him the right answer. Because he's also a winner if he gets the jack of spades first, which is a 1 out of 52 chance, and the ace of spades second. See, this has to do with what Kate and I were talking about. We were talking about, does the order matter here? No. So it turns out that if you go ahead and do it your way, where you say, okay, that works then. So if I do 1 out of 52, here, let me just do it this way. If I do 52 times 51, does that equal 1,326? No. But if I have 2 over that, I can cancel. Yeah, this is like twice as big. Do you see what I'm saying, Jim?
Yeah.
Okay. I'm going to give you one last formula. The book is also going to talk about something called 52P2. P stands for what are called permutations. Permutations are arrangements. So here the order matters. So if I take NPR, I know it's National Public Radio, but not here. We have a formula. N factorial over N minus R factorial. That's it. There's no R in the front. So we get, in this example, if we do 52P2, what do we get? Well, 52 factorial over what? 52 minus 2 is what? Yeah, it's 52 factorial over 50 factorial. And I could do the same trick I did before. If I write it out a little bit, I can see what's going to happen. It's just going to be 52 times 51. So, and again, your calculator has a button for this. If I type 52 and I hit the math key again and I go over and I want to do NPR, permutations, I'm counting how many ways can I order the 2 cards that come out? And that answer was 2652. See, that's what Jim was counting. When you said there's 52 cards for the first one and 51 cards for the second one, when you did 52 times 51, you were counting the number of ways you get a first card and then you get a second card. But see, I win if I get ace of spades, jack of spades, or if I get jack of spades, ace of spades. That's why the correct answer for me is what I get from the choosing. If that makes sense.
So that's just the broad.
These are the number of orderings. You take out 2 cards, and when they come out in a different order, you count them differently. That's why it's twice as much. Because if I get jack and ace, or I get ace and jack, I count those separately now. Whereas usually when you play cards, you don't care what order you get them. You just get 2 cards, you pick them up and look at them. Right? So that's why permutations means we're counting the orders. Combinations, we're just counting the groups. So I have some exercises for you on the group work that are going to talk about all of the ideas we talked about here, plus maybe 1 or 2 more. Okay? So I'll pass that out now. You can work on them. I'll collect the cards when I give you the worksheets, okay? And then we'll talk about them more when we're done. Let's talk about the group work a little bit as a class, and we'll see where this goes, okay? Question 1, we had the word, what was it? Parsley. Oh yeah, arrangements. Now when you see arrangements, what does that tell you? Some factorials are involved, right? Now you don't have to do it this way. You could just write them all out. Right? There's one. How many are there? 5,040 of these different words because 7 factorial. Yeah, so you know what? I am glad we have some counting techniques because I don't want to do that the rest of the class. Okay. Now that was question 1. Now question 2 says, take 4 letters from the 7. From the 7. And it says we are counting the number of what? Arrangements. I want you to understand that arrangements, that's also permutations. So some people took combinations. See, here's the thing, guys. When you take combinations, you're saying that the order doesn't matter, right? Take a look at these 2 words I wrote up here. One way of doing this, one way of coming up with a number of ways of doing this would be this. Take the 5,040 words in your list, okay? And then for each of those 5,040 words, just underline the first 4. And if you did that, you'd get all the 4-letter words there are. So are there 5,040? Well, wait a minute. There's not 5,040 because if I had this word in the list, P-A-R-S-Y-E-L, partial. What's the 4-letter word you would get from this arrangement? Same, P-A-R-S, right? Do you see that? So are there more than 5,040 or less than 5,040 arrangements of 4 letters? Less. Now here's a question. How many less are there? Well, I guess what else could I do with P-A-R-S? I could do P-A-R-S-Y-L-E. I could do P-A-R-S-L-Y-E, right? Basically, if I had P-A-R-S and I had these 3 letters rearranged in any way, I'd still get P-A-R-S for the 4-letter word. Do you guys follow that? So if that's the case, it's less than 5,040. You have to divide. Make it smaller. I think they gave up after all. Where's Jeff? And where's Tristan? That's how you want it. Hi, we're having class right now. Hey guys, let's see if we learned this. How many different ways can I arrange those last three letters? How many different ways? 3 factorial. So for number 2, we're going to take 7 factorial and divide by 3 factorial to get the right answer. But wait a minute, wait. Some of you guys said you had another way to do it. You did 7p4, which means 7 factorial over 7 minus 4 factorial, doesn't it? Juliet, you all right? You look so upset.
No,
I mean, when you start getting that, and they're not even looking at the screen, then I know I'm in trouble. Are you all right?
yeah.
Okay. Is this okay? So we have 7p4? Don't talk that way in my class. So what was 7p4? Did you guys calculate it? 840? There are 840 arrangements. Now, why isn't it 7c4? For those of you that thought it was 7c4, let me ask this. See this word here, PARS, and this one, APSR? Are they the same word? How many say those are different words? How many say those are different words? Okay. Now, if they were cards and I dealt you those 4 cards and you picked them up, you'd say you had the same hand, though. It's the same group. All right? So if you were counting groups, you'd have to count these guys the same. So you'd also have to divide by the 4 factorial ways of arranging this. And that's why NCR is 7 factorial, not just divided by the 3 factorial, but it's also divided by the 4 factorial. Okay, so it's smaller. This was not the right answer to number 2. It was the right... This formula comes up, I think, on the back, right? Let's go to the back. Let's go to the back. We'll come back to the front next. All right, question 4. Question 4, part A, says, what's the number of 6-person committees you could do? Oh, 3-person committees? And how many people are there altogether? So you guys did 11, choose 3, right? What'd you get when you did 11, choose 3? 165 possible committees. Okay. Part B. Ouch. Okay. In order to do Part B, it would really help if I had taught you something that is in Chapter 5. And I almost did, because I don't... Remember how I took the first 3 chapters and I mixed them all up, the order we went through them? I almost did that here, and I didn't, because I wanted to try and see how this book works. But the next section we're covering, by the way, I'll just say something about it now. 5-2, you're going to talk about what are called random variables. Random variables. You guys know what variables are, right? Because you took algebra. What are variables? X or Y? Yeah. And when you use variables, you want to say what X represents. So watch how I'm going to do Part B. I'm going to say let X be the number of women on my committee. Does that make sense to you guys? X can take on some different numerical values. By the way, what could X equal? What are the possibilities? X could equal 1. X could equal 2. X could equal 3. I don't think X could equal anything more than that, though. Because it's a 3-person committee, right? Is there another possibility? This is what Annette's group was doing. They said, hey, you could also have X equals 0. I count 2 ways to do this problem. remember, this was a problem that said, in Part B, they say, we want at least one woman, right? We want at least one woman. So we could say, we want little x, my random variable. How do you write at least? Bigger than or equal to 1. That's what we want, right? We want one of these things to happen. Right? We want one of these things to happen. Here's another way to say it. And this is what I covered last time when I talked about at least. We don't want x to equal what? 0. Now, how many different three-person committees are possible? 160? Oh, wait. 165, right? Okay. Will all of those have women on them? No. Some of them will have 3 men. You guys with me on that? Okay. So instead of figuring out all the ways of having 1 woman, all the ways of having 2 women, and all the ways of having 3 women, probably the easiest way to do this is to figure out how many committees would have no women, would just be men. And I claim that's an easier problem. The reason I claim that's an easier problem is because I know how many men there are. How many men are there?
6.
And how many men am I going to choose? Well, you said 2, but I'm saying if I wanted to do it the backwards way, the complement way, we want all 3 to be men, right? So the number of ways of getting 0 women in this problem is 6 choose 3. 6 men, choose 3 of them. What does that give me? Where'd the 6 choose 3 come from? It's the complement, right? So let me write it in red so you can see what I'm saying. Getting 0 women means choosing what? 3 men. Does that make sense? Who follows that? This is not easy. You had to be clever to think of this, and you had to think about the at least thing we studied last time. But if I'm going to get 3 men, how many ways are there of doing it? Well, there's 6 men altogether. I will choose 3 of them. Now, what does that equal? Let's see. 120 over 6. Does that equal 20? Did anyone calculate it? That equals 20. Okay. So, this is what we don't want. We don't want any of those 20 committees. So what is the answer to Part B? The answer is 145. Very clever. There's 165 altogether, but 20 of those committees are made only of men. So there's 145 that have at least 1 woman. I'm going to show you another way to do this, though. You don't get it yet, Craig? All right. Let me show you another way to do this, then. Okay? Let me show you guys another way to do this. I almost showed this way first, because in some ways what I'm about to show you is more direct. If you want to compute the ways of x being bigger than or equal to 1, let's compute the ways that x equals 1, then we'll compute the ways that x equals 2. Then we'll compute the ways that x equals 3, and we'll add them together. Okay? Now watch. If I choose 1 woman, how many women were there? That's 5 choose 1. But I need to multiply that by the number of ways I could choose 2 men. How many ways could you choose 2 men? 6, choose 2. The multiplication rule says if you're trying to do this and that, we're trying to choose 2 men and choose 1 woman, then that's this. Now, I have to work out what these numbers are. 6, choose 2. I don't know if you've been doing this. Here, clear it out. 6, math, choose 2, 15. Okay, so this is 15. Am I going too fast on the calculator right now? No? Okay, good, because you've seen this, so I want to go fast so that we can get to the math instead of the calculator. 5, and I'm going to choose 1. How many ways can you choose 1 from 5 people? I should have known that. If you have 5 people and you're going to choose 1, how many ways can you do it? I knew that. I didn't need a calculator for that. All right. So, how many ways could I choose 2 women and 1 man from this group of people? 5 times 15 is 75. But see, we also want to count the committees that have, let's see, 1 man and 2 women. So let me do that. That'd be 6 choose 1 and 5 choose 2. Oh, wait a minute. 6 choose 1? I know what that is. What's 6 choose 1? 6. Now, I actually know 5 choose 2 also. Do I want to go into why I know that? Probably not. 10. 5 choose 2 is 10. So this is 60. And over here, what do we want to do? This is having 3 women. So that'll be 6 choose 0, right? No men. And 5 choose 3 women. Now that's confusing to some people. The choose 0 is very strange. All right, how do you choose 0? Let's try it. 6. Here, let me do this. Let me clear this out. I'm going to do 6 choose 0. Do you know what it equals? Oh, it equals 1. There's one way of choosing nobody. If you don't like that, just trust me, it's 1. Because if you multiplied by 0, then the answer would be 0. So that's no good. Okay? So 6 choose 0 is 1. So we're going to do 1 times, and did anyone compute 5 choose 3? 10. Okay, so there are 10 ways of getting 3 women. There are 60 ways of getting 2 women, and 75 ways of getting 1 woman. And sure enough, if you were to add those up, what would you get? 145. But I really like the clever solution of saying, hey, let's do the complement here, and it's faster. And I think that this is a very good example for kind of helping you with the homework you did for today. That's exactly what they did. If they had to compute a probability, sometimes it was hard to compute, so they computed the complement instead, and it made it easier. I like that problem.